Greetings to respected faculty. I am Lasya Mandapati from CSC AI&ML D section. My roll number is 24951A6686. And today I'll be presenting on the topic Minesweeper from the perspective of design and analysis of algorithms. This is for the complex engineering project. Now, at a first glance, Minesweeper seems just like a simple game. Most of us have probably played it casually. But when we analyze it computationally, it turns out to be a very deep and complex problem. In fact, Minesweeper is not just a game, it is a classic example of computational problem involving search, constraints, and complexity theory. In this presentation, I will show you how concepts like graph traversal, constraint satisfaction, and NP completeness are directly applicable to solving Minesweeper proofs. Let me briefly walk you through the structure of this presentation. We begin with the abstract, followed by an explanation of what Minesweeper is and how the rules work. Then we move into the problem statement, which formalizes the game as a computational problem. After that, we explore important design and analysis concepts such as brute force, graph-based search, and constraint propagation. We also discuss the NP completeness of Minesweeper, which is a key theoretical result. Finally, we analyze complexity, implementation strategies, and results. Now, what is Minesweeper? Minesweeper is a puzzle where the goal is to identify all the hidden mines using numerical cues. Each number represents how many mines exist in neighboring cells. While the rules are simple, solving a game optimally requires logical reasoning and inference. From an algorithmic perspective, Minesweeper can be analyzed using graph theory, constraint satisfaction, and computational complexity. A key result in theoretical computer science, driven by Richard Kane, shows that the Minesweeper consistency problem is NP complete. This means that in general case, solving Minesweeper is computationally intractable. Minesweeper is played on a grid of size n into n. Each cell is either safe or contains a mine. When a cell is safe, it shows a number from 0 to 8, indicating how many of its neighboring cells contain mines. If a cell shows 0, it triggers a cascade reveal, automatically uncovering adjacent safe cells. The cascading behavior is very important because it directly maps to graph traversal algorithms, which we'll discuss later. The rules of the game. The rules are straightforward. Clicking a mine ends the game. Safe cells reveal numbers, and players can flag suspected mines. The objective is to reveal all safe cells without triggering a mine. From an algorithmic point of view, the important concept is consistency. A board is consistent if there exists at least one arrangement of mines that satisfies all revealed numbers. Determining this consistency is actually a complex computational problem. We can define two main problems. First, Minesweeper inference, identifying which cells are definitely safe. Second, Minesweeper consistency, checking if a valid configuration of mines exists. These problems can be formalized mathematically using constraints. Each numbered cell creates a constraint on its neighbors. For example, if a cell shows 2, then exactly 2 of its neighbor cells must be mines. This transforms the game into a constraint satisfaction problem. Minesweeper involves multiple algorithmic concepts. First, graph traversal. The grid can be treated as a graph. Cells are nodes. Edges connect neighboring cells. Second, constraint satisfaction. Each number defines a constraint. We must find the values that satisfy all constraints. And third, complexity theory. The problem is NP complete. No non polynomial time solution exists. So, the Minesweeper is a great example that combines theory and practical algorithms. Brute force approach. Simplest approach is brute force. We consider all possible configurations of the mines. If there are a h hidden cells, we check all 2 to the power of h combinations. So for each combination, we verify whether it satisfies all constraints. From this, we can determine which cells are always mines, which are always safe. However, this approach is extremely inefficient. For larger boards, the number of possibilities becomes astronomically large. So, brute force is only useful as a baseline approach. We can model the board as a graph. Each cell is a node connected to its neighbors. When a zero cell is revealed, we use BFS to explore all connected safe cells. This is called a cascade reveal and it runs on the order of n into m time. DFS can also be used in solving, especially for backtracking. DFS explores possible configurations and prunes invalid ones early. Constraint propagation is a smarter approach. Instead of checking all possibilities, we use logical rules to reduce the search space. For example, if a cell needs two mines and has exactly two hidden neighbors, both neighbors are mines. If all required mines are found, remaining neighbors are safe. This allows us to solve many parts of the board efficiently without guessing. However, when ambiguity remains, we need additional methods like backtracking. A major theoretical result is that Minesweeper is NP complete. This is proven by Richard K. in 2000. He showed that any Boolean circuit can be transformed into a Minesweeper. This means solving Minesweeper is as hard as solving SAT problems and other NP complete problems. This explains why some boards require guessing, because no efficient algorithm can solve all cases. Let us analyze its complexity. For brute force, time is of the order of 2 to the power of h into n into n, which is completely impractical. Next, constraint propagation. It is much faster and works well for simple cases. SAT-based solvers. It is the best practical performance. Still exponential in worst cases. This shows the trade-off between accuracy and computational cost. The implementation involves multiple steps. First, represent the board as a matrix with of the order of n into m. Second, use BFS for cascade reveals. Third, apply constraint propagation iteratively. Finally, use DFS or backtracking when needed. This hybrid approach balances efficiency and correctness. Results show that constraint propagation alone solves around 40 to 60% of simple boards. For harder boards, we need probabilistic or hybrid approaches. Advanced solvers combine constraint logic and probability based guessing. This demonstrates the practical difficulty of the problem. Thank you for your time and attention. I hope this presentation has helped you understand the complexity of the Minesweeper game and also has helped you understand how algorithm design applies to real world problems and even to games like Minesweeper. Thank you.